So today we will discuss about the spinorial generators of Lorentz group. In the previous class, we have seen that the Lorentz group is basically identified with the relation amongst its generating operators or the algebra. So we had seen previously that the Lorentz transformation matrix come out three different rotations and three different boosts. So ultimately there are three rotation generators and three boost generators. We have seen the examples of rotation matrices in the vector representation, which are these three matrices which are doing rotations about x-axis, y-axis and z-axis. And similarly, there are three boosts matrix of transformation, which are boost along x-axis, y-axis and z-axis. And corresponding to these, there are generators which will tell us along what direction the transformation has been made. For example, if I want to know what is the generator of this matrix, the rotation about the x-axis, what I will do, I will take the matrix itself, do the derivative with respect to the parameter of transformation, which is theta in this case. Then I will obtain a new matrix after the derivative, and then in that matrix I will put the parameter to 0. So that will give rise to the generator of the rotation along about the x-axis. And we are supposed to get, after this operation, which you can verify as an exercise, the first matrix over here, sorry, not the first matrix over here, first matrix over here, the red matrix, is the rotation about the x-axis. Similarly, if I do the rotation about the y-axis or the z-axis, take the corresponding transformation matrix, do the derivative with respect to the parameter and put the parameter to 0, I am supposed to generate these remaining two generators of the rotations. These are the three generators of rotation matrix acting on vectors. These are the vector representation generators. Similarly, for boosts, there are three boosts along x-axis, y-axis and z-axis. Do the following operation. Take d lambda upon d parameter of boost beta, obtain the new matrix and put the parameter to 0. And that will give rise to the three boosts generator, which are these three matrices. So this overall gives you six generators of Lorentz transformation, three boosts and three rotations, which collectively are written as a m mu nu. M mu nu is supposed to be some antisymmetric rank 2 tensor. An antisymmetric rank 2 tensor has 6 independent components in 4 dimensions. As you might have seen for electrodynamics, there was a antisymmetric rank 2 tensor F mu nu, if you are familiar with that. That had 6 components, 3 magnetic fields and 3 electric field. Any antisymmetric rank 2 tensor has 6 components. All the diagonal entries are 0 because antisymmetric tensors diagonal elements are 0. So M00, M11, M22, M33 are 0. Surviving entries are M01, M02, M03, M12, M23 and M31. These are the 6 components which are surviving and they are antisymmetric. That means M10 is minus of M01, M21 is minus of M12 and so on. So there are 6 independent components and these 6 are the 6 matrices. And as we have seen previously that these 6 matrices are related to each other in terms of the Lorentz algebra. So 3 of them are rotation, 3 of them are boosts, and boosts and rotations talk to each other through the commutation relation which we had written in the previous class. So these objects, rotations commutator is supposed to generate another rotation generator. Boost commutator is supposed to generate a rotation generator, and boost and rotation commutator is supposed to generate a boost generator. So this is the relation between the 3 J's and 3 Y's, and you can verify the relation what we had written above are indeed satisfied by these 6 elements. So you can verify the algebra which we have written, call this one as y1, y2, y3, y1, y2, y3, and this 3 as j1, j2, j3. You will realize that the algebra which we had written previously above are exactly satisfied by these 6 matrices. So therefore they are generators of the Lorentz group. They are the generators of the Lorentz group in 4x4 dimensional space. They are vector representation. Now in order to go to the spinors, we are looking for a spinor representation of the Lorentz group. That means I want a matrix D lambda which acts on spinors. These matrices, the Lorentz transformation generated by these matrices are obtainable from these generators, will act on the 4 vectors t, x, y, z, or p0, px, py, pg. These are the vector representations. So these Lorentz transformation matrices which are generated by this m mu nu. Remember, the lambda we had written as e to the power iota theta dot j and minus, so let us say minus was common. Let me write it cleanly. Remember, we had written it as e to the power minus I theta dot j minus eta dot y. This is how our general Lorentz transformation matrix is written. 3 j's come with 3 thetas, or call it beta, this one, and 3 y's come with 3 betas. Collectively, in terms of m mu nu, there can be written as exponential of omega mu nu and m mu nu, where omega mu nu is also 6 component object made up of 3 thetas and 3 betas, and m mu nu is made up of 3 j's and 3 y's. So collectively it is written like this, sometimes with iota, just to account for the group structure or algebra where we had written. So therefore I have written the lambda like this. So the game is clear. You have to find out the generators acting on your space. For example, for vector space, for vector representation, these are the 6 m mu nus which we have obtained, and they satisfy the same algebra which we had seen for rotations and boost matrices, which we saw in the previous class. The question is how to write the same thing for the spinor space, or d lambda half of representation. Previously we had seen that the spinor representation can be factored into a double copy of the rotation group, which is written as spin half representation. So double copy of spin half representation is equivalent to spinorial representation, and therefore I'm calling it a d lambda half of representation. This is also a 4x4 dimensional matrix, but this is acting on a spinor, the spinor which has 2 copies of spin half objects, xi1, xi2, xi3, xi4. So these 2 are spin half objects. Put together they generate a spinor of half rank, and this still being a 4x4 dimensional, a 4x1 dimensional vector like a t, x, y, z, they do not transform as vector, they transform as spinors. That means they transform with a different matrix, d lambda half, and what this d lambda half will be obtainable from their generators. Okay, so therefore in the spinorial space we are looking for again 6 generators of the Lorentz algebra, because the algebra has to remain same, so therefore there should be 6 generators, and which act upon the spinorial objects. Now again, since this is not a course on a full field theoretic and representation, so therefore I would not be deriving those properties for you, but I would just be listing down in a spinorial space what are those 6 generators. So we are familiar with the gamma mu matrices. Gamma 0 was supposed to be beta, and gamma i's were supposed to be beta times alpha I. These were the matrices which we had written down. The statement is, if I take the collection of gamma 0 and gamma I as gamma mu and take the commutator between the 2 gammas, gamma mu and gamma nu, mu can take any value, nu can take any value, then I obtain a 2 index object, one with mu, one with nu, because I can take any value of mu and I can take any value of nu. So this is a rank 2 object because 2 indices are appearing, and this is anti-symmetric as well because commutator is anti-symmetric. So therefore I have generated a rank 2 anti-symmetric object, and my claim is that this satisfies exactly the same algebra which these m mu nu satisfy. So remember, this has 6 pieces in it, 3 rotations and 3 boosts, and they satisfied a relation amongst themselves which was suitable for Lorentz transformation. The claim is that if I take this set S mu nu, that also has 6 components, S0i, S01, S02, S03, and Sij, S12, S23 and S31, just like what M had. So those 6 elements of S mu nu also exactly satisfy the same algebra which 6 components of M mu nu satisfy. So therefore this is also a valid representation of Lorentz transformation generators. And therefore these are the things which will act on spinors. So this acts on a spinor in the sense of Lorentz generation of matrices. So the S mu nu are the generators of transformation. The D lambda matrix, which is given by half half, will be obtainable from exponential of I omega mu nu, the same omega mu nu, rotation or boost, whatever amount I am doing. And then the generator will change. The amount will not change. If I am doing rotation by 30 degree, the parameter will take the value 30 degree. But what matrix will do the 30 degree change will depend upon which representation I am talking about. So in spinors, this S mu nu will go and sit. In vectors, M mu nu will go and sit. In function space, as we saw, there was this X cross P kind of operator which was going and sitting. So fine. So in spinor space, this S mu nu's are generator, exponential of that with omega mu nu's the Lorentz transformation matrices for spinors. And let us try to do some simplification to see their structure clearly. So first, the 3 component S0I, S01, S02, S03 are to be written as 1 by 4 times gamma 0 and gamma I commutator. So 0 and I. So here 0 and I were appearing, mu and nu were 0 and I. So therefore the commutator will have a 0 and I. Which is, if I open it up, it is just gamma 0, gamma I minus gamma I, gamma 0. Now we know that gamma mu and gamma nu satisfied the something called Clifford algebra, if you remember, minus of 2 eta mu nu identity operator. Okay, so if I take mu is equal to 0 and nu is equal to I will get a gamma 0, gamma I, and right hand side I would have a eta 0 I, which is 0. So therefore gamma 0, gamma I is equal to minus of gamma I, gamma 0, and use this fact to write the commutator into 1/2 of one pair, gamma 0, gamma I. The second pair is the negative of the first pair, so they add up. So 1 by 4 becomes 1 by 2. All right. So let me clean it up. So we have this structure S0I. The first 3 operators of the Lorentz transformation generators for spinors are half times gamma 0, gamma I. Okay, where gamma 0, if you remember, was the beta matrix itself, which is identity cross identity and minus identity along the diagonal, and gamma I matrix was beta times alpha I matrices, where alpha I had sigma matrices along the anti-diagonals. So as a result, gamma I has a sigma and minus sigma along the anti-diagonals. Okay, so that is the S0I. So we can write down fully what is S0I, half times gamma 0, which is this, and gamma I, which is this. So ultimately you will get S0I is half times sigma I along the anti-diagonals. What more, if I take the dagger of this S0I, this sigma I and sigma I will be done complex conjugation with and Hermitian transpose with, and will be replaced along the anti-diagonals. So you will get sigma I dagger along the anti-diagonals. But since polymatrices are Hermitian, I can convert it back to sigma I. Therefore, S0I, the generators are Hermitian matrices. Just like M0Is were also Hermitians. Further, there is a unique identity which connects S0I with its dagger in some sense. So what I do, I just multiply gamma 0 from left and right to S0I. So S0I was half, which is here, times sigma I along the anti-diagonal, which I am writing in the middle. And then I squeeze it between gamma 0 from the left and gamma 0 from the right, which is here and here. So once I do that, this is a simple algebra. You can just pay attention to matrix multiplication and you will see that once you do that, you will get minus sigma I and minus sigma I along the anti-diagonals. Okay, you have to just be careful. This is 2 cross 2 dimensional matrix identity. This is also 2 cross 2. This is also 2 cross 2. This is also 2 cross 2. 0 is also 2 cross 2. Empty 2 cross 2 matrix, dimensional matrix. So everything is 2 cross 2. You have to do it slightly carefully. This means 1 0 0 0 0 1 0 0 0 0 minus 1 0 0 0 minus 0 minus 1. Similarly, for this you can write the 0 you have to write for, let us say we are writing sigma z. Sigma z would be 1 0. There is a minus outside present, so minus 0 1 here, and then here the same thing, 1 0 0 1, and then 0 0 0 0. So that is this. So you have to just do it carefully and you will be able to recover that. If I put gamma 0 from left and right and squeeze S0i with gamma zeros, what I will get is minus sigma I along the anti-diagonals, which is the minus of the dagger itself. The dagger was sigma I, so was S0i itself, but I'm writing in a convenient way because that will become clear. The region of that will become clear. So if I squeeze if I squeeze S0i with gamma 0, what I'm getting at the end is its dagger with a minus sign. Okay, this is for the first three generators of the Lorentz transformation on spinors. What about the remaining three? The remaining three are Sij. Again, by the definition, it is gamma I, gamma j, and same Clifford algebra which we had discussed. For I not equal to j, I will obtain gamma I, gamma j multiplied together with a half factor. The similar way the 1 by 4 was converted into 1/2 for the previous case. Let us write down what is gamma I and what is gamma j. Put together, you will get a diagonal entry. Minus sigma I, sigma j along the first diagonal and minus sigma I, sigma j along the second diagonal. So that is the Sij for you. For example, S12 will be minus of sigma 1, sigma 2, 0, 0, minus of sigma 1, sigma 2. Similarly for sigma 2, 3, sigma 3, 1, and remaining things are minuses of each other. Again, you can see that it is also Hermitian. You take the dagger, you will see that it will come back to itself. Sorry, if I do the Sij dagger, you do this, you will see that sigma I, sigma j will be replaced by sigma j, sigma I. So you see here, minus sign is there, sigma I, sigma j is there, and here also we have a sigma I, sigma j. So you see that it is sigma, this was sigma I, sigma j, this is sigma j, sigma I. So again you see they have not, up to sign this is fine, but they have not come back to itself. Sigma j, sigma I is not equal to sigma I, sigma j. So again, we have not been able to generate a Hermitian transformation. Remember, Lorentz transformations were not being generated by Hermitian matrices. Even for vectors, if you recall, we had in the previous class, we had seen that the Lorentz transformations boosts were not unitary matrices. That means they were not being generated by Hermitian matrices. The same thing is happening even for a spinorial representation, that the boosts generated by Sij are not Hermitian matrices. Okay, fine. With this realization, we again do the same thing which we had done for S0i. S0i, we had squeezed it between gamma 0 and gamma 0. Do this again. Put a gamma 0 to the left and a gamma 0 to the right. Do this again, matrix multiplication with care. This time it will become clear what we were trying to do. It will still is Sij dagger with a minus sign. What have we done to recapitulate? We had previously seen S0i and S0i dagger are equal to each other. They are Hermitian. So rotations are generated by Hermitian transformation. Therefore, rotations are unitary transformations. And rotation generators squeezed between gamma 0 became the minus of its Hermitian conjugate. Boost generators are not Hermitian, but still boost generators squeezed between gamma 0 do become minus of their Hermitian conjugate. This is a very important relation which has an implication for the next line which we are going to write. Okay, so now for spinor representation, we want to know the matrix which operates on spinor state to do a Lorentz transformation. And with the prescription of the generators, they have to be exponentiated with the parameters of transformation. I'm going to write this d lambda as this. So, okay, so there are a couple of notational issues. One should be very careful in order to make sense of the next steps. So I have written iota upon 2, that 2 can be ignored. So this is just a bookkeeping parameter many textbook use. So in principle, you can forget about the 2. So let me erase the 2 out from here. And one more thing apart from this extra 2 I had initially written in notes, which I could have avoided. So let me just emphasize. First, let us forget about 2, that was immaterial. Secondly, when I'm writing this, the transformation matrix as generators times the parameter times iota, then this iota, whether I write it explicitly here or I absorb in omega, depends upon the notations we are writing. So here, when I have written the transformation generators as 1/4 commutator gamma I gamma j, typically in that sense the Lorentz transformation matrix d lambda is written as just exponential of omega mu nu s mu nu. However, if I want to write down in terms of iota omega mu nu, then many of the times people would write a minus iota in front of this as well. So with any of these definitions, we can go ahead. So we should be slightly careful when we write in a consistent notation. Since I had chosen to write the Lorentz transformation for vectors as with iota, I'm trying to do the business with the same thing over here for S mu nu as well. So since I'm going to write as with iota, let me supply back iota here in the definition. Okay. So then effectively it would be this. And therefore you will see everywhere when we were taking a dagger, the iota which was present will become a minus iota. So ultimately this will become a minus iota, so it will become a plus over here. Okay, so there are two relations which you can obtain either with iota or without iota, depending upon which way you are writing the transformation matrix. So one way we can stick with the without iota definition where we have derived all these properties, or in order to make sense with the textbook notations where various textbook use, I can go back to plus iota. Then I will correct all these equations which are getting with a minus sign. They will become a plus sign. Either way you can do business. So for the time being, let us stick with the deviation, meaning let me not use the textbook notations people use the notations we were using, 1 over here, 1 over here. That means I can just forget the iota over here as well. So let me erase the iota out as well. So we will just use the notation which we have been using. So let me first remove all the iotas, and then we will get back to how to generate transformations out of it. That doesn't matter. Only thing you have to be careful when you insert an iota over here, in order to compensate for that iota's extra insertion, the generator should also accommodate a minus iota somewhere. So, but since I am going to work with this S mu nu without any iota here, I'm going to use the definition of transformation without iota here as well. Okay. So if this is fine, let us go ahead and see what do we get. If d lambda is there, d lambda dagger if I do, I should get this omega mu nu S mu nu dagger, which is fine. But I know S mu nu dagger is in general minus of S mu nu squeezed between gamma 0. So I will get a minus sign here. So S mu nu dagger is equal to minus of S mu nu squeezed between gamma naught from both sides, which is fine. Now Taylor expand this quantity. I will get a one identity minus this term here, which is gamma naught omega mu nu S mu nu gamma naught. Then the square of this quantity, so 1/2 factorial, and this quantity twice appearing. So you see all the terms have a very similar kind of a structure, where identity can also be written a gamma 0 from the left and gamma 0 from the right, because gamma naught identity times gamma naught is again identity. So all these terms have gamma naught from in the left and gamma naught in the right. This term has a gamma naught in the left, gamma naught in the right. This term also gamma naught in the left and a gamma naught in the right. In between there is a gamma naught as well, which together combines and gives you identity. So you see the structure is that there is a gamma naught, then identity minus omega mu nu S mu nu plus 1/2 factorial, the twice product of omega mu nu S mu nu, and gamma naught and all higher order terms. So you see ultimately you are going to get a gamma naught and exponential of minus of omega mu nu s mu nu, and gamma naught at the end as well. So therefore, you are going to get, after taking the dagger, gamma naught, the inverse transformation. This was plus. The direct transformation matrix comes with a plus signature. The inverse transformation comes with a minus signature. So you get a d lambda inverse gamma naught gamma naught. So therefore, the identity which we have landed up with is this, that d lambda dagger is not d lambda inverse. Had it been a unitary transformation, then it would have been true. But all the Lorentz transformation are not unitary transformation. So therefore, gamma naught extra multiplication you have to live with. Only if it were rotations only, then the dagger would have been equal to inverse of the transformation. But since it is involving boosts as well, which are not unitary transformation, therefore a gamma naught extra has been come about. So irrespective of which notions, which iota version or without iota version you work with, you will always land upon this property. So I have shown you without iota, but if you work with iota, you have to correct this and previous terms as well, and you will land upon this identity once more. So this is a well-defined, understood identity that Lorentz transformations on a spinorial index, the dagger of that is not inverse of itself, but a gamma naught squeezed version of the inverse. Why have we derived that? Because if I write down the gamma bar, remember we were trying to find an inverse quantity. We were trying to write down a Lagrangian, but xi dagger psi was not a Lorentz invariant object. Now we can see why. Because when we do the transformation of Lorentz transformation, psi will transform with d lambda of psi. Psi dagger will transform with a d lambda dagger of psi. And since these quantities are not inverses of each other, I will not get identity back, and it will not transform as invariant quantity. But now you can convince yourself that if I work with a quantity called psi bar, which is psi dagger gamma 0. So psi bar psi, if I see how does it transform, it has a gamma naught in between. So psi will transform with a d matrix, psi dagger will transform with a d dagger matrix, and I have a d dagger gamma naught d in between. That in between I can insert. So I have dagger, I know already is equivalent to inverse squeezed between gamma naught and gamma naught. So you see, in between I get a double gamma naught, a pair of gamma naught, which will become identity. So what you have to do, you have to just write down d dagger as gamma naught d inverse gamma naught. There was already a gamma naught present, which will become identity. So ultimately you will get gamma dagger, psi dagger gamma naught d inverse d psi, and d inverse d is identity again, and you will get back gamma naught psi dagger gamma naught psi, which is equal to psi bar psi. So this quantity is invariant. This quantity psi dagger psi was not invariant. It was not going to psi dagger psi, but psi bar psi goes to psi bar psi under Lorentz transformation. So this is an invariant quantity. Similarly, if I look at this quantity over here, which is the first term in the Dirac-Lagrangian we were trying to write down, psi dagger gamma mu psi mu psi. This was again not Lorentz invariant. But if I correct it to psi bar gamma mu del mu of psi, then you will see that due to the fact that, which will be clear in a minute, that if I do the transformation, this psi bar will pick up a d dagger inverse. This del mu will transform under Lorentz transformation as a covector, so it will have this transformation law, and this psi will transform as a matrix transformation is like this. Okay, so overall you will see, you can just combine, you will have a psi bar on the left, this d dagger is equivalent to gamma naught d inverse gamma naught. Then there was already a gamma naught which is present here, so this will be this gamma mu which is already there, which is there, lambda inverse which will appear from the transformation of the derivative operator, which will appear over here, and then there is a d lambda which is position independent, so it will come out of the derivative, and then there is derivative hitting the psi. So all these terms will appear if I take the transformation of the first term of the Dirac-Lagrangian generalized to psi bar. Now use the properties that two gamma naughts put together is identity, and effectively you will get from this thing, this is just a number, this is a matrix element, mu element of lambda inverse. This is just a number and this is a matrix. So number and a matrix can be flipped together. So I can take this on the left hand side and bring it on the right hand side. So this becomes here, d lambda appears here, and I have this structure d inverse gamma mu d lambda. So I had a gamma mu matrix. What I am going to do, I am taking a transformation matrix d inverse from the left and d on the right, and one can prove, which we will see in a minute, that this operation is equivalent to something like a Lorentz transformation as a vector on gamma nu. Gamma nu is not a vector, it is a matrix, but still this operation is equivalent to what a Lorentz transformation would have done to a vector. Lambda mu nu, this is the vector representation of the Lorentz transformation that combines with gamma mu. Remember, a genuine vector v mu undergoes under Lorentz transformation as lambda mu nu v nu. The same thing is happening to gamma mu. Despite it is not a vector, it is a matrix. So it transforms with a d inverse of matrix from left and d of the matrix from the right. End product is that it is almost the same thing as a vector would have transformed. It's 4 matrices. Previously 4 components get combined with these numbers. This time 4 matrices will get combined with these numbers. So this transformation is equivalent to this. And once I have proven the quantity in the box, then you will see that this quantity will churn up a lambda mu nu of gamma nu, and there was a lambda inverse of nu mu coming from the derivative Lorentz transformation. They will cancel each other. So first let us prove this identity and then be done with that. That is 1 minute job. You can just take the Lorentz transformation matrix gamma mu. You have to identify the 4-dimensional representation generators where these 6 elements, which we had written previously as well. But to start with the spinorial representation. Do not work with m mu nu, start with the s mu nu. Remember, when I'm going to do d lambda inverse from the left, d lambda from the right, it is the spinorial representation matrix I have to work with. So you start with a spinorial representation from the left, a spinorial representation from the right. Do this algebra. This is a fairly straightforward algebra. Use the anti-symmetric properties. You will see that the quantities which will be appearing in this will be the S mu nu matrix and gamma nu matrix. Commutator will appear as the first term. Now, here is the crucial identity, which is an exercise for you to prove that S alpha beta and gamma mu, these are 2 different matrices. Gamma nu is nth matrix of 4 gammas. S alpha beta is one of the generators, S01, S02, S03, or S12, S23, S31, one of these. Put together, it is equivalent to identifying one of this 2 index identifies the M alpha beta. Out of these 6, which one is this? So if this is 01, then it will pick up this 01. And the mu component of this will appear over here, and the new component gets summed over. So there is a nice identity which is there, which I'm just going to write it down. And that is the crucial thing in proving the identity, that S alpha beta gamma mu can be proven to be M alpha beta, and then its mu index remains free and the new index gets summed over. This is an identity which you can prove, or we will see it in a minute. But if this is the case, I can replace the commutator appearing over here by the M alpha beta. Now this M alpha beta is the vector representation 4 cross 4 dimensional matrix. And therefore you can see that the first term was a gamma mu, the second term now is the same parameter but with the M matrix now and the gamma nu. Together it can be written as an identity matrix multiplying gamma mu, and then this matrix multiplying gamma nu, and this is just an expansion of the exponential, if you recall, which is nothing but the vector representation of the Lorentz transformation. So I started with a spinor representation of Lorentz transformation, put the d inverse and d from the both sides. I use an identity which I have not proven, but it is easy to prove, that the commutator of the spinor representation generators and gamma mu leads to a vector representation generator. S was the generator for the spinor transformation, gamma mu was a gamma mu matrix. Their commutator generates a matrix which is 4 cross 4, but this is a generator of the Lorentz transformation in the vector representation. So ultimately the whole thing over here becomes a vector representation of Lorentz transformation. Okay, so this is a straightforward algebra. There's nothing much to look at. Only thing has that you should prove this identity, which is which we will do in the next class to sum up with. But ultimately, if this is true, that this identity is true, then you can go back, use this identity over here. Therefore, this will become a lambda mu nu gamma nu, and this lambda mu nu and lambda inverse nu mu will give me a identity matrix. They are inverses of each other, and you can prove from there that psi bar gamma mu del mu psi again is a Lorentz invariant quantity like a psi bar psi. So therefore, both the pieces previously both of terms were appearing in the Lagrangian of a Dirac particle with psi dagger. Here it was psi dagger and here it was psi dagger. Those things were not Lorentz invariant, but I corrected them to psi bar rather than psi dagger, and ultimately all these things fell into place, and I have a invariant Lagrangian at hand. So from the next class we will quickly wrap up the discussion on this identities which I have written, and then we will proceed from the Lagrangian, which is a Lorentz invariant Lagrangian. Okay, so I stop here.